things to study about these relations. You cannot follow some ideas from the classical case because these objects didn't exist. You don't have clubs in omega. Okay. So why is that moving? Okay, here. So reduction. So I just mentioned the word reduction. So let's define reduction. So you have two spaces, x0 and x1, are of the form theta to the kappa. Let R0 and R1 be binary relations over x0 and x1 respectively. Now we say that a function f from x0 to x1 is a reduction from R0 to R1 if and only if for every eta and c in x0, eta and c are related in R0 if and only if f eta and fc are related in R1. Okay, so okay, we denote this by the hook arrow. So two comments here. The first thing is that basically at this point, reduction is just comparing the number of equivalence classes at this point. So we need to demand more about the function. And the second I want to mention is about the hook arrow. And this is because you have the quasi-order smaller or equal. So we need some kind of different symbol because otherwise you will have some term that is saying smaller equal, smaller equal, smaller equal. So that's why I changed the notation, the usual notation, let's say. Okay, so let's demand more on the function. So Lipschitz reduction, this is the most demanding one. So we have the two spaces x0 and x1. We have two binary relations. Now, we define for eta and c in the Baire space, we denote delta eta c, the minimum alpha, such that eta alpha is different than c alpha, or in case they are always equal, it's just kappa. Now, we said that a reduction f of R0 to R1 is one Lipschitz. It's for all eta and c in x0. Delta eta c is more equal than delta f eta fc. So now this is very strong. We denote this by the hook arrow sub 1. And you can also ask the function to be just continuous or just Borel, or if you really want some kind of like weak, not to demand too much, you can demand bare measurability.
This one Lipschitz would correspond to, you know, a very strong form of continuity for the usual product topology. Yeah, okay. And I assume you will say a lot of things when the reduction is one Lipschitz. It's really preserving a lot of information, one would assume. Or
yeah, it's very, very strong. If it's one Lipschitz, it gives a lot of information.
Are you going to give examples of these reductions, like which ones are one Lipschitz or are not one Lipschitz and so on?
I will show that stationary reflection gives one Lipschitz, and indeed phase reflection is going to give one Lipschitz reduction.
Okay.
So let's see. So now you can talk about reducing one relation to another. So you can reduce the equivalence model non-stationary in the Baire space or in the contour space. So one result, this result took, it's very, I don't know how to say, it took a lot of time to write. It's not difficult, but no one paid attention. So if every stationary subset of X reflects at a stationary many alphas of Y, then the equivalence modulo X is continuous reducible to the equivalence modulo Y. And then you can see that here is when we start using stationary reflection. And another use is by Friedman, Hütten, Kulikov. If you are working in L, X is a subset of kappa and Y is a subset of regulars of kappa, are stationary sets. If every stationary subset of X reflects the stationary many alphas of Y, then you can get the same reduction, but in the contour space. So you can see that the stationary reflection is useful to compare this kind of theories. But the problem of this is that you have some limitations, because the stationary reflection is something that is, let's say, strong. You're using full reflection, that every stationary set reflects. So let's just go through some limitations. So let lambda be a regular cardinal and denote by S sub lambda, the set of alphas is smaller than kappa, so that the cofinality of alpha is lambda. So one limitation is that for all regular cardinals, gamma is smaller than lambda is smaller than kappa, X subset of S lambda, then X does not reflect at any alpha in S gamma. Like you cannot reflect to a smaller cofinality. You can avoid the big cofinalities in small clubs.
Sure.
So you can only, stationary reflection can go from reflecting a cof omega into cof omega 1, but not cof omega 1 into cof omega, or things like this. Another limitation, obviously, if you have a square, it is known that square gives you a set that does not reflect at any alpha of smaller than kappa. So you can destroy stationary reflection by square, the full stationary reflection by square. And this is the case of L, for example. Another one is that for all regular cardinal lambda smaller than kappa, and you take a subset X, subset of S lambda, X does not reflect at any alpha in S lambda. You cannot reflect the same cofinality into a same cofinality. The same reason of when you try to reflect into small cofinality, you can avoid it because you only need one element that is lambda cofinal, and that is just the limit of the club. So you don't have this. And the last one is that the full stationary reflection usually requires some kind of large cardinals to get it. So the idea is to overcome these limitations, because we would like to compare the equivalence modulo non-stationary without thinking about how big is the cofinality. We want to go to omega cofinal. And for example, you don't have a notion of what is something to be stationary when the cofinality is omega. You don't have a club in omega or in omega cofinal ordinals. So this is where fake reflection is coming from. So the first, now let's go to the definition, the big one, the filter reflection. Any questions so far? Okay. So let's start by the case of L. So if you let's study the equivalence modulo non-stationary in L. So denote by the equivalence, the equal sub lambda and in theta, the relation equivalence modulo S when S is the lambda cofinal ordinals. So it was proved that in L, if lambda is a regular cardinal below kappa, then for all stationary X subset of kappa, the equivalence modulo X is continuously reducible to the equivalence modulo lambda in the Cantor space. So the question is, why do we have here in L? How is this possible if there's no reflection? There's no fully reflection in L. And also, we only demand lambda to be a regular cardinal below kappa, so lambda can be omega. So we don't have a notion of stationarity. We don't have full reflection yet. So there's something that must be going on in there. So let's start by trying to understand the case of L. So let's start by defining capturing clubs. So suppose S is a stationary subset of kappa, and we take a sequence of F alphas indexed by S. It's a sequence such that for every alpha in S, F alpha is a filter over alpha. Now we say that the sequence F capture clubs if and only, sorry? No, okay. So the sequence F capture clubs if and only if for every club C, the set alphas, or the set of alphas in S such that C intersected alpha is not an element of the filter F alpha, is non-stationary. So basically, you can think about the sequence F alphas as the club filter sequence. So let's take a look to that. So for any alpha smaller than kappa that is not omega cofinal, denote by cup alpha, the club filter subset of alpha. And now just define the F alphas as the club filter. So club filter, everything in the filter, in the club filter is a club because we're not in omega confinal. So obviously, so if you take a club and you restrict it to some alpha that is not omega confinal, obviously C intersected alpha, if alpha is a limit point of C, then it will be in the club filter. So we are just trying to make more general the notion of the club filter with these capturing clubs. And now, so basically the elements of F alpha are what we will understand as clubs. Now, if you have clubs, you can talk about stationarity. So now we can talk about filter reflection. So take X and S, stationary subset of kappa. And then you have and then take a sequence of filters of alpha over alpha. Now we say that F reflects to S if and only if F capture clubs, and for every stationary subset of X, the set of alphas in S, such that Y intersected alpha belongs to F sub alpha positive is stationary. So here, I don't know, can you see the hand when I move the hand?
Yes, yes.
Right.
Although okay, did you give us the positive would be positive for each one of the filters? So that'd be, but I have I may have a question later, but please go on.
Okay, so yeah, so as I was saying though, so basically what you're saying here is that the alphas in S, such that Y intersected alpha intersects all the elements of the filter, is stationary. So remember that F alpha, the elements of F alpha is what we understand as clubs in alpha. It doesn't have to have all the clubs. We don't know how they look, but if it captures clubs, then we can think about them as clubs. So if Y intersect alpha intersect all the elements of F alpha, then it's somehow we can understand it as a stationary set. So we are reflecting because Y intersected alpha is intersecting everything that we now try to understand as clubs. And this is the definition of filter reflection. And finally,
sorry, I have a question. What is F alpha plus?
F alpha plus are the sets that intersect all the elements of F alpha. That intersection is non-empty.
It's so if you think of this as a measure, it'd be like the positive. So being positive measure would be me being in the filter. So this would be all the alpha. So it would be all the alphas in S, the stationary set, that somehow are positive for each one of the notions of stationarity you have at each level alpha somehow. You have one notion of yeah. Okay.
It's okay.
So you think you're putting together a lot of measures.
Yeah. Okay. Okay. So finally, we say that X filter reflects to S if and only if there is a sequence of filters F over a stationary subset of S, so S dash, such that F reflects to S dash. So we don't want the whole sequence to be indexed by S. We just want it to be indexed by a stationary subset of S. So we're just trying to mimic what does it mean to be a club, what does it mean to reflect, what does it mean to be stationary, and this is like the least we need. Okay, so let's make some comments to try to understand this better. So let's take X and S, stationary subsets, such that for every alpha in S, alpha is not omega cofinal. And now let's suppose that X and S, you have fully reflection. So this means that for every Y subset of X, Y reflects the stationary many betas of S. So if you take the F alpha to be the club filter, then this is then talking about F reflection. It's just talking about the stationary reflection, because now the filters is the club filter, and you were demanding to intersect all the elements of the club filter, basically, of the elements of the filter, and in this case, is the club filter. So stationary reflection is is a special case of filter reflection. And when the filters are the Klopp filters. Now we call fake reflection the case in which X filter reflects to S, and for all alpha in S, F alpha is not a superset of the Klopp filter. So it is indeed, it has to be a subset or something, but you don't have the Klopp filter. So X fake reflects to S if X filter reflects to S, but is not witnessed by the Klopp filter. That's what we call fake reflection. That's the part that we're going to focus on.
So you have some notion of reflection, but it somehow misses. I mean, it is kind of orthogonal to stationary reflection in some sense, because at each alpha in S, it somehow will reflect, but not in the correct set, so to speak, or in a strange notion. Okay.
Yeah.
Huh.
Yeah. So fake reflection is that you have this filter reflection, but it's not the stationary reflection, because the stationary reflection is just one particular case of filter reflection.
But it's kind of very far away from stationary reflection.
Yeah.
Because it says you're actually missing the right notion because you're reflecting F alpha, but F alpha does not contain the Klopp filter on alpha. Then you're actually reflecting kind of in the wrong place, or so to speak, or in different places, not in a.
Yeah. You're dropping out. Imagine you have the Klopp filter, and then for every Klopp filter for the Klopp filter in alpha, you start dropping the Klopps that you are miss when you try to intersect. So you're taking a very small filter compared to the Klopp filter.
Okay. Yeah. You're kind of changing the topology of reflection, so to speak. Okay.
So now let's another comment about the stationary filter reflection. So suppose S is a subset of kappa and you have a partition of S. So now define the filters of alpha by, for every alpha in S beta, you take F alpha to be the filter generated by beta. So the principal filter, everything that contains beta. If beta is smaller than alpha, otherwise just take alpha, this trivial filter, and that's fine. So in here, you can say that this sequence of filters first will not capture Klopps. This will not capture Klopps, but somehow reflects, because every X, let me see if I wrote, So if you take Y subset of X, then Y intersected alpha belongs to the intersect of the elements of alpha only depends if beta is an element of Y. And eventually you will reach a point in which beta will be an element of Y intersected alpha. So it will be stationary, but it will not capture Klopps. So the thing is that filter reflection, if you divide the two parts of filter reflection, the capturing Klopps and the reflection part, both are in CFC. You can get them in CFC, either by Klopp filter that they capture Klopps, or by this very trivial way of reflecting, but it's very difficult to get both at the same time by the same sequence of filters. Okay, now another some strong forms of filter reflection. So we say that X strongly F reflects to S if and only if F capture Klopps, and for every stationary subset of X. Now we demand that Y intersected alpha not only intersect all the elements of F alpha, but we also demand Y intersected alpha to be an element of the filter F alpha. So in that sense, it is stronger. And there's also another even more strong way, and is that you can add a diamond sequence. So we say that F reflects with diamond to S if F capture Klopps. You have a diamond sequence Y sub alpha, so that for every stationary Y subset of X, the subset of S in which you guess y and y intersected alpha belongs to f positive of alpha is stationary. Now this is even stronger than this. You can prove that this one implies this one. So these are the three notions of filter reflection. Now, okay, so now let's move to fake reflection. Is there any question? It's always a weird feeling just to be talking by yourself and not hear people.
Yes, I assume you're going to compare these notions of reflection and give us some flavor of how they interact also with other applications of reflection or something like that.
Yeah, I'm going to show, because at this point it's very abstract. We don't know if it holds, like if you can have fake reflection without having a stationary reflection, applications to generalized descriptive set theory, and some other kind of comments about some stuff that you can get from fake reflection.
Okay.
So let's now focus on fake reflection when we don't have a stationary reflection. So a property of filter reflection is monotonicity. So if X filter reflects to S, then you can take a subset of X, and is Y, if filter reflects to a superset of S. This also holds for strongly filter reflection and for filter reflection with diamond. Now, the first thing that appears that you can find is that suppose X strongly filter reflects to S. If diamond X holds, then so does diamond S. So you can obtain diamond S just by strong filter reflection and diamond X. So this is something that you can get from filter reflection. But now let's go more to what we were interested, the reduction part. So fake reflection and reduction. So if X filter reflects to S, then indeed, oh, there's a typo. So if X filter reflects to S, then the equivalence modulo X is Lipschitz reducible to the equivalence modulo S in the Baire space. That's why it says kappa S. Okay. It should be S super kappa. Okay. And the proof is very, yes? Okay.
It's fine.
Okay. So the proof is very similar to the stationary reflection. So suppose you have the sequence of alpha, this is filter reflection. Now, for every alpha of S dash is the subset of S that with the filter reflection, define the equivalence, I don't know how to call that symbol, tilde alpha over the functions from alpha to kappa by saying that eta is alpha equivalent to C if and only if there is an element of F alpha such that W, so that W intersected X is a subset of the beta smaller than alpha in which eta and C coincide. Now it's easy to see that this is just an equivalence relation. So we know that there are at most kappa to the alpha many equivalence classes, and we assume in the general descriptive set theory that kappa to the with kappa equals kappa. So we can assign a code, an ordinal to each equivalent class, and then we will just denote it by this number, let's say. And finally, now you can just define the reduction. So you can say that F goes from the Baire space into the Baire space by saying that for all eta in kappa to the kappa and alpha smaller than kappa, F eta alpha is equal to either the code of eta restricted to alpha, the equivalence class of that, if alpha belongs to S dash, or 0 otherwise. So the point here is that if eta and C, if eta and C are related, then there is a club in which they coincide, the C intersected S dash. I don't know if...
Yeah, because that's, I mean, you had, so where's the club from? Because you have W is from the witness somehow, or, you know, in the witness in sequence, then, and you know that W intersect X is a subset of the coincidence set of eta and Xi. So what? So
yeah, the thing is, okay, so it's just that I wanted to change the screen, but I cannot because of I'm sharing. But so suppose eta and C, they are related in this modulo X. So there is a club such that C intersected X is contained in the where they coincide.
okay.
But now we know that the first property of filter reflection is that it captures clubs. So for club many alphas, C intersected alpha is going to be in F alpha. So W is going to be just the club intersected alpha, the club that witnesses that eta and C are related.
Oh,
So that gives one direction. And the other direction is given by the second property of filter reflection, that one that if eta and C are not equivalent, it is because they are different on a stationary set, in a stationary subset of X. But if they are different on a stationary subset of X, you can reflect it to a stationary many subsets. So there are alphas in which there is no W in F alpha witnessing this property, this relation. So basically you have just shown that capturing clubs give you the same code for club many, and stationary, the second part, the reflection, give you different codes for stationary many. So this is the idea of the proof. Okay. Okay. So we know this. It indeed is generalized the result from stationary reflection. But now the question, what happens in L? So in L, we know that we have the reduction, but we don't have the stationary reflection. And we know you don't have a stationary reflection in L, but you have the reduction in L, as we saw before. So what happens about fake reflection? Do we have fake reflection in L? That means suppose V equal L does X, F reflects to kappa for all stationary X subset of kappa. Can we show that in L? So to answer that, first we need to introduce a diamond principle, a reflection diamond principle. So we say that a set N, and take some sets N and X. We say that N sees X if and only if N is transitive, primitive, recursive, closed, and X union singleton X is a subset of N. So N see X and the singleton X. Now let's, this is going to be a bit technical, but I hope it's fine. So for a stationary set S and a positive integer N, we define DL star sub S by 1N, the principle that asserts that there is a sequence N indexed by S satisfying first that for every alpha in S, N alpha has a cardinality smaller than kappa and C is alpha. The second is that it guesses. So there exists a club for every X, there exists a club C, such that for all alpha in C intersected S, X intersected alpha belongs to N alpha. So you can see that here it looks like capturing clubs, because you can take, it's a bit more general, because if you take X to be a club, basically it's capturing clubs, more or less. And the third one is that for every pi1n sentence phi valid in a structure kappa membership AM, some predicates, then there are stationary many alphas in S, such that N alpha has the size of alpha, and N alpha believes that phi is valid in the small structure alpha membership, the restriction of the predicates. So now, tell me.
Yeah. So this 3 is somehow given some kind of pi1 and indescribability of yeah, very strong. No, it's much stronger than indescribability, because you don't just reflect something below your kappa, but to stationary many alphas, where somehow the formula, I mean, if the formula holds above, then it also holds below. So it's like, yeah, Vadim, sorry.
No, sorry. I just because you're saying above that N is a set, but you assume it's a model of set theory.
Yeah, yes. I mean, at the end, it will be a model of CF minus, if I'm not wrong.
But
Well,
when you
maybe
say that in the lowest line, you mean that N alpha is considered to be equipped with the epsilon relation?
Yeah,
What
I
does
think
it
you need the epsilon. Yeah. You need the epsilon relation, yes, because I mean it's PR closed.
Yeah.
This part I don't understand at all. What was it? Primitive recursive closed? Like it's oh.
Yeah, what is PR closed in this context? It's a transitive set.
No PR in the context of natural numbers, but this seemed to be.
Oh no, but you can also apply it in set theory. I think it just transferred to the language of set theory, a notion of being primitive recursive. Oh, I see. But you need some sort of I mean, you know, like barwise kind of. Yeah. It's what is PR closed, Miguel? In this context?
I think you have this primitive recursive function that, for example, I think, for example, when you construct L, if I'm not wrong, you have this rudimentary function on this kind of functions.
Yeah, it is, I think, in that sense.
In that sense, yeah.
So
I think N at the end, it is indeed a model of CF minus, just that in this way you can, I mean, you can state it this way, but obviously you will need the membership, because N alpha must be able to see something of the small structure. So N alpha needs to see the membership relation.
But it also needs to see validity, because N alpha, you know, the last line is N alpha thinks that phi is valid. So you need to be able to have enough set theory to define satisfaction relation. And that, I mean, you don't need modes of set theory for that. You need much less than that, but you need, you know, the PR closed is perhaps exactly what you need to define some kind of fake notion of satisfaction. And that is what is reflected also from kappa to the N alphas. And it is also able to see that alpha behaves as some mode of something, or some phi. But this is a very strong, I mean, these three, you call it very technical, but I find it very interesting because it has this sort of a large cardinal flavor, kind of in the neighborhood of, you know, weakly compact is pi 1, 1 in describability. And this is kind of similar, except as Vadim says, you have to be much more careful with the N and N alphas, because they are not quite like V kappas and so on, but they are much weaker moles. But the behavior is exactly like in large cardinals in this number 3.
Yeah.
But then, but you have pi 1 N, and then you have stationary places where it reflects correctly. So okay, please, but go ahead.
No, yeah. I mean that's basically the point, because if the N alphas, they cannot be model of CFC, because then you would have precisely large cardinals. Because then you will have, like, if N alpha is V alpha, then basically you have large cardinals.
Sorry, is AM a subset of kappa?
Yeah.
Okay.
Yeah. Okay. Okay. So now this diamond principle, we have that DL star S pi 1, 1. It will imply fake reflection. But now, after I suppose that discussion, you already imagine it. So suppose S is a stationary for which DL star S pi11 holds, then for all stationary X subset of kappa, X filter reflects to S. So the idea of the proof is the second part, the second condition of this DL star S was very much club capturing, so we only need the reflection. But for the reflection, just take a phi, be a pi1 sentence such that alpha membership models or believes phi if and only if phi is regular. This sentence exists. It's regular in the big model, let's say phi, or in our case, it's going to be an alpha. So we just take the S dash subset of S, the ordinal such that n alpha believe phi is valid in alpha membership. So that means that n alpha sees alpha as a regular ordinal. That's all we're saying. N alpha sees alpha regular. So now for every alpha in S dash, we just take F alpha as the set, as the club filter in N alpha. So the elements that N alpha believes are a club of alpha.
Okay.
So again, N alpha has enough set theory to think about clubs and to see many things, but not enough to see that they are indeed not clubs. Because if alpha is omega cofinal, N alpha see alpha as a regular. So N alpha doesn't know that there's no thing as a club filter in omega cofinal ordinals. So what N alpha sees is some kind of filter that behaves somehow like clubs. And
but you may also have such N alphas strong enough, as you say, to see that something is a club, or to make sense of that definition, yet being so bad as well subset theory that they have a lot of fake cardinals, a lot of like things that are ordinals but they believe are cardinals because they don't see enough functions, and they have a lot of like descending sequences of ordinals that they cannot really it is a very weird model of some kind of fragment of set theory, yet somehow you tag to each alpha whatever n alpha sees as a club. That's very that's very powerful. That's a very nice thing.
Yeah. So and then the reflection will follow from pi1n reflection. Okay. So now we know. Let me move this away. So now we know that this diamond DL star S pi11 will implies fake reflection or filter reflection, because if this n alpha has a lot of set theory, it can see the actual filters, club filters. Okay. So let's move to, okay, so fake reflection in L. So what happens is that if you suppose V equal L, then for all n smaller than omega, and every stationary subset of kappa, DL star S pi1n holds. So this was precisely what's happening in L. The weird reflection that many people use in L was this DL star S. For every n, it holds. So as a corollary, then for working in L, for every stationary subset S of kappa, kappa filter reflects to S. And now if you use monotonicity, what happened? Wait, does it move? Monotonicity, if you're still working in L, then for every stationary sets X and S, X filter reflects to S. So we have indeed filter reflection in L always for every X and S. So now we can go to see what have we gained from, okay, I'm missing one last part. Yeah, this is just a comment that in particular, now we have a notion of S reflecting into S, and even more, we have that S omega 1 filter reflects to S omega. So we can just reflect into the same set and reflect even to smaller cofinalities. Just give me a minute that my phone is ringing. L, we put inside this. Okay, so now let's check the list of limitations we had about stationary reflection. How does it look now for filter reflection? So the first one is that full stationary reflection is a special case of filter reflection, as we already saw from the beginning. The second, so we know that stationary reflection, you cannot reflect to a smaller confinality. You cannot reflect S omega 1 to S omega. But we indeed already show that it's consistent to have S lambda filter reflects to S gamma. Doesn't matter which one is bigger or smaller. Now, we know that square destroys full reflection. You can get a subset that doesn't reflect, but you have a square in L, and we had fake reflection in L. So fake reflection is consistent with square. For all regular cardinal lambda, you can talk about S lambda reflect to S lambda. It's consistently true. We already saw it in L, and again, in full reflection, it doesn't hold. You cannot reflect it to the same set. I think there's one last one. Yeah. And finally, you don't have large cardinals in L. So fake reflection does not require large cardinals. But now, the thing is, we only know at this point that fake reflection holds in L. And the question is if you can force it. Okay, this is the case of L. Yeah. So let's go to the forcing part. So the question, can we force filter reflection? There are two answers. The first one is the easy one. Just force full reflection. It's a particular case of fake reflection, of filter reflection. Collapse a weakly compact cardinal or do one of those things to, yeah. It's a stationary reflection is a particular case. Yeah.
No, that's quite natural. I mean, it's especially after this discussion on the way you're really. I mean, the weakly compact has much more reflection, of course. In the yeah, okay.
Yeah, but so
the sort of collapse you would do, Miguel, would be what kind of a Levy collapse, or kind of more like a Mitchell type of a collapse, where you want to be more careful about the way you preserve things, because you need to preserve in the forcing. You need to preserve enough, notion of truth. I don't know if plain Levy collapse will be too strong.
I think Levy collapse is enough.
Is enough? Okay.
I think so.
Yeah, because there are some cases where we want to, like for instance, if we want to collapse, like in the classical case, weakly compact, but keep the tree property and collapse the weakly compact, say to Aleph 2, then of course it'd be very far away from being weakly compact, but it keeps the tree property, but it needs to collapse in a very careful way. You need to do an iteration where you kind of spread the collapse in such a way that you do collapse, but you keep most of the property. Well, you keep at least that property. But here, I think Levy.
I mean, Levy is one way of getting it. There is also.
No, but Levy is too. I mean, Levy collapses immediately, and it kills the weak compactness in a strong way. And sometimes it may be too strong. It may be too fast in a way. Sometimes, I mean, one can see these things as weakening forms of compactness in mole theory. And this discussion is kind of connected to something that was discussed by Javier Caicedo here, and maybe some other people also in previous lectures. You kind of, I mean, when you have weak compact cardinal, you have kind of almost full compactness in some sense. And then you kind of want to weaken it and to spread it out. And the stationary reflection or full reflection or this filter reflection is like forget about full compactness, but keep some of the structural features of compactness, and reflection is one of those. So maybe, yeah, I don't know. That's an interesting thing. I asked this question because I'm always interested in this forcings where you start with some large cardinal, you have some nice property like compactness or something else in mole theory, and then you want to preserve some of that and maybe keep some of that property in some logic or somewhere, But then I know I have to be very careful in the way I collapse. That's why I asked this question.
Yeah, I mean, there's this. I think I don't remember what's the name of the forcing, but that you can get full reflection from Malo cardinals. I don't remember the name of that forcing. I think it's from Shella and someone else. I don't remember precisely. Okay. So, I mean, but okay, come back. So the actual question is if we can force fake reflection, like forcing the reflection, filter reflection, without forcing the full stationary reflection. So for that, we will need another diamond. So we will use Sakai's diamond plus plus. So the definition of this, sorry? Okay. So the definition of this diamond is just, so we have the diamond plus plus sub S as a stationary. It tells us that there exists a sequence of K alphas satisfying the following. First, K alpha is a set of size alpha, the size of alpha. Second, X, for every X subset of kappa, there exists a club of kappa such that for all alpha in C intersected S, C intersected alpha and X intersected alpha belongs to K alpha. So up to this point, this is the definition of diamond plus. And now the third condition is saying us that this set written there is a stationary in H kappa plus of weaker than kappa. So the elements of H kappa plus of size smaller than kappa, such that M intersected kappa belongs to S, and the collapse of M membership is equal to K sub M intersect kappa membership. So this is the double plus thing. And now so the trick is that diamond plus plus implies DL star S pi 1n for every n. But I'm here stating just to pi 1 2 just to give an idea how is the proof, but in general it's for every n. So for every stationary subset S, diamond plus plus S implies DL star S pi 1 2 or pi 1L. So as the sketch of the proof, take a sequence that witness the diamond plus plus, and now define the n alphas as the primitive closure of K alpha union alpha plus 1. So this way you ensure that n alpha is primitive, closed, and it sees alpha, because now you have alpha and alpha the point and the alpha the set. So now take phi any pi 1 2 sentence and some predicates AM, such that K so the model K with membership and the predicates, they believe phi. Now give an arbitrary club C, take the set of M's that are elementary substructure for H kappa, so that M intersected kappa, it's an element of the club C, and the predicates are in M. The good thing is that this new fancy C, it's a club. It's a club in H kappa small sets of H kappa plus. So now, okay. So we continue. So now by the second part of diamond plus plus S, we know that if C is a club, then the intersection with the set that the diamond plus plus, say it was a stationary set. So now we know that this set is stationary. Now the only thing that we need to prove is that every M in this set, then M believes phi in the sense of, if we take any M there, then they will believe phi after the collapse, after the transitive collapse. So we know that by assumption, kappa membership and the predicate believe phi. By definition, that means that H kappa plus believe that the small structure believes phi. This is just a notation, just to make it more precise. But then by elementarity of M, because M is an element of C, and so M is elementary, so we know that M believes the same. So we can do the transitive collapse. So we have that pi is the collapse of M into N alpha. So N alpha believes the same. And okay, so we know that N alpha is going to be the collapse, because N alpha, we defined it like this. It was the how you call it, the closure. But so if it's the collapse, then it will coincide. So it is the transitive collapse, and so N alpha believes that the small structure believes phi, and that is what we wanted. So now we know that diamond plus plus implies diamond star S. The diamond star, the DL star S pi 1, 2. In general, pi 1 n, you just put more variables. So we only need to force diamond plus plus S. And this, we're lucky, it's done already by Sakai, the same paper that he defines diamond plus plus. So let S be the poset of all pairs K, B with the following properties. So K is a function such that the domain of K is smaller than kappa. For each alpha in the domain, K alpha is transitive model of CF minus of size at most alpha or aleph 0, with K restricted to alpha, an element of K alpha. So you can see here that it has to know some set theory. Yeah. Then B is a subset of the power set of kappa of sizes smaller or equal to the domain of K. And now the order that we're going to use is just that K dash extends K, B dash extends B, and for every element of B and every alpha in the domain of K dash that is not in the domain of K, B intersected alpha is an element of K dash alpha of the structure K dash alpha.
So you put the reflection somehow into the forcing definition.
Yeah. Somehow you start putting some kinds of the elementarity, and you're trying to start pushing that way. So, and this is Sakai proof that with this forcing you can force diamond plus plus S. So we know how to force diamond plus plus S. So we know how to force DL star S pi 1 n, and that implies that we know how to force fake reflection. So as a corollary for all stationary subset X and S of kappa, there is a small d kappa closed, kappa plus CC forcing extension in which X filter reflects to S. Thank you.
Great. Thank you very much, Miguel. Okay, we went a little bit over time, but it's fine. Maybe you want to stop sharing the screen the same way. Okay. Perfect. Entonces, okay. So, well, that's. So I have some questions, but let us see if somebody in the audience has questions for Miguel. Questions?
So I have a question. That's okay.
Yes. Yes.
And Miguel, you spoke about the construction of quite a few of these sequences, especially the special diamond you constructed. How do you know that these actually exist?
Initially, the first one that constructs something like this that I know, well, I have, okay, there are many constructions that in L, one construction was what Friedman hit in Kulikov to prove something in generalized descriptive set theory. But even before that, Devlin constructed this kind of sequences for diamond sharp when he was working to diamond sharp. But the problem with diamond sharp is that you cannot get diamond sharp above ineffable cardinals. So you need to be a bit more work to have it in all in L. So that's somehow how the intuition was working.
Thank you.
Okay.
Yeah. Any other question by somebody else? No, just kind of vague question. So, in principle, I mean, going back to Vadim's question on these n's and the n alphas and so on, this kind of fake notion of satisfaction, fake notion of fake modes, of fake reflection, as you called it. Do you have a measure of when you have real reflection, like from large cardinal, say weakly compact, or even better reflection from pi 1n, indescribable, and so on? How far? I mean, is there some kind of in between this very fake notion, but that you have, say, in L, and these other notions that are so far away from L? Can you measure the degree of correctness? Does it make sense? I ask this question because in some of the earlier applications of these sort of things, it makes some sense. Like, you might have some instance of fake reflection, but you may also know that for some alpha 0, the notion is correct up to the degree you want. That you have some kind of correctness, that it is not really speaking about, I don't know, fake cardinals or fake clubs or fake, completely fake, but in some area, in some local area, you may want to know that they are correct, even if the rest of your notion is still quite fake. Do you have any situation like that where you kind of strengthen or weaken the fakeness, at least locally, and still, can work in L or kind of close to L? Because this sort of thing is related to all these things of weakening compactness or end extensions of models of set theory, or that.
I think the way you can measure this, if how many of these F alphas are the actual Klopp filter, or how far is the filter to the Klopp filter.
Yeah,
it's probably the way you can measure it.
Because at the moment you seem to have two very kind of disjoint scenarios. One where you have reflection, all this theory of reflection that has been done, and it is like a way of dealing with compactness in a very refined way. And then you have the fake reflection, and the origins of that sort of thing. It's all this Kistler theory of end extensions, which is also about some kind of forms of compactness, where it is kind of like for L omega 1 omega, or places where you don't have compactness, and how can you extend models? And then you extend models by doing things that are in spirit, not too far away from this sort of reflection. I mean, you do reflection kind of the other way around by taking an end extension. And then you immediately enter into problems that, because it is not true compactness, you extend the models, but you may end up with wrong notions of some things. And that's very interesting. But here you seem to be pushing that, all the way to reflection principles, much farther away. And this sort of in between, maybe do fake, but be correct here, might become relevant. I don't know. This is just a thought. I don't know.
Yeah, I mean, you can. If there is a stationary subset, the filters is the Klopp filter rather real reflection. But I don't know how else to measure like how fake is the reflection.
Yeah, I don't know. So is there any other question by anyone? More questions? Okay, so thank you very much, Miguel, and thank you all for being here this time. I find this work very interesting, and Okay, we have some logic coffee people want to join. I will be back in about 2 minutes. I will stop recording.